Today we're going to be taking a look at section 10.6, which is on thermochemistry in Chemistry 2. And enthalpy by definition is the energy produced or absorbed by a given reaction. And we're going to let enthalpy be represented by the letter H, capital letter H. Remember that enthalpy is a state function, which means it doesn't depend on the path that's taken but the current state of the system. I know we've covered this before, but this symbol, triangle here, delta, means change in. So the change in enthalpy can be equal to the amount of heat, which is Q, as long as we're at constant pressure. So the change in enthalpy at a constant pressure is equal to the heat given off by the system or absorbed by the system, which brings us to looking at whether we have an endothermic or an exothermic reaction. Just to keep this in mind, an endothermic reaction is going to take in heat, so that means our delta H is going to be a positive number. And exothermic reactions give off heat, so delta H is going to be a negative number, to help keep that in mind as we go through the problems. Okay, this first example says to consider the reaction of sulfur, which is solid, plus oxygen gas yields sulfur dioxide in gas form. And it tells us that delta H is going to be negative 296 kilojoules per mole of sulfur dioxide that's formed. So it's a negative number. That's going to indicate to us that it's an exothermic reaction. And for every 1 mole of SO2 formed, this reaction is going to release 296 kilojoules of heat. So it wants us to calculate the quantity of heat released when we have 2.10 grams of sulfur burned in oxygen at a constant pressure. And oxygen in this case will be in excess. So let's take a look at what we have. Let's rewrite this so I can put the information that I want to put below it. Makes it a little clearer for me to look at. And it's important to put the states because that's going to come into play when we cover Hess's law. So this reaction is going to give off 296 kilojoules per mole of SO2. So let's write the information we have for the problem. It says calculate the quantity of heat. So I want to know delta H when I take 2.10 grams of sulfur and burn it in excess oxygen at a constant pressure. And I want to know how many kilojoules this reaction is going to give off. Well, if it were 1 mole of sulfur, it would produce 1 mole of sulfur dioxide, and you would end up with this much energy given off. And since this is kilojoules per mole for this reaction, we have to go back and we have to change grams to moles. So we're going to take 2.10 grams of sulfur, and 1 mole is about 32 grams. So 2.1 divided by 32, this is going to be 0.0656 moles of sulfur. So if this were 1 mole of sulfur, I would produce 1 mole of sulfur dioxide and give off 296 kilojoules. But I don't have that. I have 0.065 moles of sulfur, which is going to, because it's a 1-to-1 ratio, it should produce 0.0656 moles of sulfur dioxide, and that's all because it's a 1-to-1 ratio. And I can set up a ratio to figure this out. If 1 mole gives off 296 kilojoules, then 0.0656 moles gives off how many kilojoules? So we're going to cross multiply and solve for x. So 296 times 0.0656. So x equals 19.42 kilojoules. And I'm going to put a negative sign here indicating it's still an exothermic reaction. Now you look at it and say, does this make sense? Well, it does make sense because if 1 whole entire mole is going to give off almost 300 kilojoules, then it makes sense to say that about 6/100ths of a mole should give off quite a bit less, which is 19.42 kilojoules. Look at the next exercise. It says consider the combustion of propane. So C3EH8 is propane plus 5 oxygen gas yields 3 CO2s and 4 H2Os. And the delta H for this reaction is 2,221 kilojoules for completion, and it's exothermic because it's the negative sign in front of it. So let's see what they want us to look at. So assume that the heat comes from the combustion of propane. Calculate delta H where 5 grams of propane is burned in excess oxygen at a constant pressure. And wants us to calculate delta H. So the first thing we have to do, because this goes by multimole ratios instead, we have to change 5 grams of C3H8 to moles. So we're going to come down here and take 5 grams times the mass of C3H8 is 44 grams per mole. We take 5 divided by 44 and get 0.114 moles of C3H8. This reaction says that in order to get this, I have to burn 1 mole of propane to get 2,221 kilojoules given off. I don't have 1 mole, I have 0.114. So let's do a ratio. So 1 mole of C3H8 is to 1.114, as 1 mole is going to give off 2,221 kilojoules, and I want to know how many kilojoules this is going to give off. And let's just reason through it to begin with. This is 1 mole, and this is about 1/10 of a mole, so this number should be considerably less. So we cross multiply and take 2,221 times 0.114, and X ends up being about 252.4 kilojoules given off, which is the number that we expect to see because of the size difference in the number of moles. And remember, that's a negative sign, not because the value is negative, but because it's exothermic and gives off heat. The last thing we're going to look at in section 10.6 is calorimetry, and this is one that's made with very expensive equipment, styrofoam cups, and we can actually use this to measure the enthalpy in the reaction in the calorimeter. So we use this, and because we know what the substance is in here, and we measure the enthalpy in the form of the temperature difference, which is in the form of heat that's given off, we can calculate the delta H for this reaction. And it may be possible for us to look at this reaction and another reaction and actually add those two and combine those two in order to find what the enthalpy change would be in a final reaction that we really can't carry out in our lab. And we'll talk about that tomorrow with Hess's law.